Hello students, welcome to the class. So in the previous class we had discussed regarding the need for the classification of the elements. We have seen Dauber-Reiner's law of triads, Newland's law of octaves, Mendeleev's periodic law. We have seen the merits and demerits of the law also. Why it was not successful, we'll understand it here. Coming to the modern periodic law. The modern periodic table, it is developed after periodic law, and a periodic table was given by Mendeleev. Yes, after Mendeleev gave his periodic law and periodic table. In the latter part of 18th century, Mendeleev made his periodic table. Scientists did not know about the internal structure of the atom back then. That till then, internal structure of the atom was not known. Yes, what does that mean? Till then, all of them considered as atomic mass the fundamental property of an atom. Yes. So the development of various atomic models and advances in the quantum theory revealed that atomic number is the most basic property of the chemical element of an element. This led to the modification of Mendeleev's periodic law, which is today called modern periodic law. So we know what is atomic number. The atomic number is equal to the number of protons or electrons in a neutral atom. After knowing the fundamental unit of an element, that is the atomic number, scientists now had a clear idea about quantum numbers and electronic configuration of the elements in the periodic table. After knowing the periodic law, chemists noticed that there is an analogy between the 94 naturally occurring chemical elements. This analogy made people more curious about the chemistry of these elements. And scientists made various artificial elements too. A new periodic table was developed based on the modern periodic law by modifying the Mendeleev's periodic law. Okay, so modern periodic law. Before going to this modern periodic law, who gave the major contribution to the modern periodic law? Yes, it was none other than Henry Moseley. Yes, this person, he is a physicist from England. In the year 1913, the whole story of modern periodic table started. Yes, what was the story all about? Was he observed that when certain metals, they were bombarded with high speed electrons. When certain metals were hit with high speed electrons, x-rays were emitted. X-rays were emitted. He found x-rays were emitted. He studied the frequencies of these x-rays emitted, and he found that in all the cases, what Henry Moseley found, the square root of frequency was directly proportional to none other than atomic number of the atom of that element. So he found that the square root of frequency, he studied the frequencies of these x-rays emitted, and he found that when you take the square root of the frequencies of the rays emitted, they were directly proportional to the atomic number. So what he did, he plotted a graph. Yes, he plotted a graph between so here what he did was, so he plotted a graph between square root of frequencies and the atomic numbers. Yes, square root of frequency I'm sorry, into 10 raised to 8 hertz he considered, and the atomic number. Yes, atomic numbers 10, 20, 30, 40, 50. So 10 atomic number, 20, 30, 40, 50, and so on. And he observed that when he plotted the graph of square root of atomic numbers and the square root of frequencies and the atomic number, he got a straight line passing through the origin. He got the straight line passing through the origin. So when he concluded, so he plotted the graph between square root of frequencies and atomic numbers of different metals. A straight line was obtained. When a graph was plotted between square root of frequency and atomic number of the metals, the graph was not a straight line. So he concluded that when he plotted the square root of frequencies and atomic masses, it was not a straight line. But with atomic number, it was a straight line. Understanding? So what did he conclude? He concluded that there was no relation between the frequency and atomic mass but surely there was some relation between the frequency and the atomic number. From these observations, Mosley therefore concluded that atomic number and not the atomic mass is the fundamental property of an element. So he concluded with his experiment that atomic number is the fundamental property of an element. This was the only mistake which was being done by Dobereiner or Newland or Mendeleev. Yes, so only their law was not getting successful. So Henry Moseley, for the first time through his experiment, concluded that it is not atomic mass which is the fundamental property, but it is the atomic number. On this basis of his hypothesis, he put forward his law of periodicity. So he put forward his law of periodicity. Yes, and he commonly called it as modern periodic law. He called it as modern periodic law because it was not the work of only Henry Moseley, and his co-workers who had also contributed to this explanation, to this theory. So it was called as modern periodic law. And this law states that the physical and chemical properties of the elements are periodic functions. Yes, there is repetition of their atomic numbers. And this law put forward came with a table which was called as modern periodic table, or it was also called as long form of periodic table. So what does this law says? When you arrange the elements in the increasing order of the atomic numbers, not atomic masses, there is repetition in the properties of the elements. So it is the basis of modern periodic table. This law is the basis of modern periodic table. Thus Moseley, what he did? He modified Mendeleev's periodic law. He modified Mendeleev's periodic law by stating this law. So he said, when you arrange the elements in the increasing order of atomic numbers, there is repetition in the properties. There is repetition in the physical and chemical properties of the elements at or after regular intervals of atomic numbers. We are frequently seeing this term regular intervals. What does that mean? Regular intervals of atomic numbers means what? Even in Mendeleev's periodic table, we had seen regular intervals of atomic masses. So what does that mean? Regular intervals means there is repetition. When you write the elements in the increasing order of atomic number, there is repetition after certain atomic numbers. It is not necessarily after so and so elements only. In first case, it might be immediately after 2 elements, there might be repetition. In next case, there might be after 8 elements, there is repetition. Yes. So there is repetition in the properties of the elements when you write elements in the increasing order of the atomic numbers. So if you consider in chemical reactions, there is a transfer or sharing of electrons. Thus, chemical properties of the elements depend on what? It depends on the number of electrons. When I say it depends on the number of electrons, what does that mean? It means that it depends on the electronic configuration. And what is electronic configuration? Writing a pattern of representing the electrons. And what do you mean by electrons? It is nothing but equal to atomic number. Yes or no? So it depends on the electronic configuration, that is number of electrons. And we know that in an atom, number of electrons is equal to number of protons. So number of protons in an atom depends on what? It is nothing but atomic number. Similarly, this is about chemical properties. Similarly, physical properties. I'm giving the explanation for modern periodic law. Physical properties of the element are also dependent on the electronic configuration in an atom. Hence, physical and chemical properties of the elements are the functions of what? They are the functions of atomic numbers. So this is about modern periodic law, which was being proposed by Moseley. And there he introduced again periodicity. So what he said, there is repetition in the properties when you write the elements in the increasing order of atomic numbers. So with this explanation of Mosley, many of the limitations of Mendeleev's periodic law was solved. Very important position of isotopes was solved. So isotopes mean what? Same atomic number, different mass number. So when same atomic number is there, all the isotopes of an element will come under one block only, because you are writing elements in the increasing order of what? Atomic numbers. So if atomic number is same, all will come under one block only. Yeah. So periodicity we have come across this term lot many times. It means what? It is defined as the repetition of, what do we call it as? Repetition of similar properties. Repetition of similar properties of elements placed where? Placed in a group. We know what is a group. Vertical column. Placed in a group and separated by definite gaps. Definite gaps of atomic numbers. Example, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, then comes sodium, and so on, then comes potassium, and so on, then comes rubidium. Getting? So after definite gaps, so after so many gaps, there is repetition in the similar properties. After so many gaps, there is repetition in the similar properties. Yes, so we call them as definite gaps, or you can call them as regular intervals. Regular intervals. So when elements were arranged in the increasing order of the atomic numbers, it was observed that the properties of the elements were repeated after certain regular intervals of, say, one element, or say two elements, or say eight elements, or say 8 elements, 18 elements, 18 elements, and 32 elements. So this was the repetition seen. This was the repetition seen. The repetition was seen after one element sometimes. It was seen after 2, 8, then again after 8 elements, after 18 elements, again after 18 elements, and then after 32 elements. And therefore, these numbers, especially 2, 8, these numbers 2, 8, 8, 18, 18 and 32. I took one because after the discovery of noble gases, two elements came into consideration. So these numbers are called magic numbers. They are called magic numbers. These numbers are the cause of periodicity, you can say. They are the cause of periodicity. That means in first case, when you write elements, first elements, hydrogen, helium, after two elements, there was repetition, lithium, sodium, potassium, then here was fluorine. Then after 8 elements, there was repetition. Therefore, here after 2 elements, 8 elements, then again 8 elements, 18, then again 18, then 32. So after these many numbers of elements, there was repetition. Therefore, they were the cause of periodicity in the properties due to repetition of what? Due to repetition of same electronic configuration. So electronic configuration plays a major role in deciding the chemical properties of the elements. Deciding the chemical properties of the elements. Yes, chemical properties of the elements. So this is the modern periodic table. You can see here, there is all the elements placed. Hydrogen, helium. So after, can you see here? After two elements, third element is having similar properties, so it is placed here. 1, 2, 3, 4, 5, 6, 7, 8. After 8 elements, there is repetition. Then again after 8 elements, there is repetition. After 18 elements, there is repetition. After 18 elements, there is repetition. Then after 32 elements, there is repetition, because LA 57, from 57 directed to 72. So these 18 plus these 14. So after 32 elements, there is repetition. Again, 32 elements. So these numbers are called what? They are called as magic numbers, because they are the cause of repetition in the properties. You can see here, these elements which are denoted with this color, they are called alkali metals. Blue, alkaline earth metals. I'll discuss one of them, one by one, all of them. Can you see these metals which are placed here? These all are called as transition metals. They are all called as transition metals. These post transition metals which come after transition metals. And here the dark purple, what you're seeing, they are called as, here you can see silicon, germanium, arsenic, antimony, tellurium. They are all called as metalloids. They are called as metalloids. These elements are non-metals, and these are also non-metals which are having typical name, that is halogens. Helium, neon, argon, krypton, xenon, radon, these are all called noble gases. Here the light violet color, they are called lanthanoids, and here dark ones are called actinoids. Yes, so all these names, these are the names, different ways of considering what are the types of elements, right? So this is the modern periodic table, which is also called as long form of periodic table. Long form of periodic table. Structural features of the periodic table. Now, how this periodic table, how it is being divided? Yes, this periodic table, it is classified into various forms. You can classify it into various forms. With the study of modern periodic law, the modern periodic table, which is also called as long form of periodic table, or it is also called as Bohr's table, because he classified the elements in the form of table. He gave this table. Therefore, it is also called as Bohr's table. The elements are arranged in the increasing order of the atomic numbers. So this is one way of grouping the elements. One is groups and periods. Yes, you can see here. What are groups? Can you see these vertical columns? Yeah. Can you observe these vertical columns? The vertical columns are called as groups. The vertical columns are called as groups. They are called as groups. So they are numbered from 1. Earlier they were numbered with 1A Roman numerals and A, B notations were used. But here with the more modifications, they are numbered with our Arabic numerals: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. So they are numbered like this. Yes, so there are 18 vertical columns in the modern periodic table, and they are called as groups. The elements belonging to a particular group is known as a family, and it is usually named after the first member. So hydrogen, always remember, it is studied separately. So when I speak about group 1, I speak about lithium, sodium, potassium, rubidium, cesium and francium. Yeah. So group 2, these are the family members of this family. Group 13, these are the members of this family. Are you all getting? Group 14, these are the members. So you can name them with the first member. I can call group 13. I can call group 13 as boron family. Boron family. I can call group 14 as carbon family, group 15 as nitrogen family, group 16 as oxygen family, group 17 as fluorine family. Apart from that, there are typical names also. So the elements present in a group are separated by definite gaps, that is our magic numbers. What are the definite gaps then? Now, so see here. The elements this which are present in a group, they are separated by definite gaps. Hydrogen 1, helium 2. So after 2 elements, lithium is there. Lithium, after the next member, sodium, is separated after 8 elements. Potassium is separated after 8 elements. Rubidium is separated after 18 elements. Cesium is separated after 18 elements. Then 32 elements. Last 32 elements. Getting it? So after 2 elements, there is repetition. I can write it like this: 2, then 8, 8, 18, 18, 32. Yes. So with these magic numbers, you can remember the atomic numbers. See, for example, lithium is 3. Lithium atomic number is 3. You want to know sodium atomic number. So after 8 elements, it is separated. So 3 plus 8 is 11. Sodium atomic number is 8. Potassium you want to know. So it is also separated after 8. So it is 19. Rubidium. It is rubidium 19, after 18 elements it is separated. So 7, it is 37. Cesium, it is separated after 18 elements again, 55. Then francium, Fr, it is separated after 32 elements. So it is 787. Can you see here? All are same. So these magic numbers will help us to understand the atomic numbers of our elements which are present in the group. Elements which are present in the group. Now, if you look at the electronic configuration of the elements present in a same group, yeah, when the elements present in the same group. For example, let me consider group 1. Group 1. Lithium is there, sodium is there, potassium is there, and so on. I'll consider these simple elements to make you all understand. The atomic number of lithium is 3, so it is 1s2, 2s1. Sodium 11, 1s2, you know to write the electronic configuration. 2p6, 3s1. So this is the outermost shell. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So if you look here, the elements which are present in a group, they have same number of electrons in the valence shell. In the outermost shell, I can say they have same electronic configuration, or I can say same number of electrons in valence shell. So same electronic configuration in valence shell, or same number of electrons in the, both are the same. So here our electronic configuration in the valence shell is 3s. Only this number is changing. Principal quantum numbers changes, but number of electrons is nothing but electronic configuration, and that is same. Yes. So their electronic configuration of the valence shell is identical. Yes. So I can represent it like this. If 1, 2, 3, 4 represent principal quantum number, I'll write it as n. So yes and 1. So all the elements, they have got same outermost configuration ns1. With this you can find for rubidium also, you will get same. Instead you will get 5s1. That's it. N changes. Due to this similar outermost electronic configuration, the elements which are present in a group, all the elements which are present in a particular group, they will have similar chemical properties. Their chemical properties will be same. They will have similar chemical properties. The chemical properties will be same. So lithium, sodium, potassium, rubidium, cesium, francium will have same chemical properties. Similarly, try to write electronic configuration for all these group 2 elements and see. They have all same valence electronic configuration. So their chemical property also will be same. So I can say that the chemical properties in a group are all same because of same valence shell electronic configuration. And when I speak about physical properties, the physical properties of the elements, say melting point, boiling point, density, they vary gradually. Yes, they may increase or they may decrease. So they vary gradually. Yes. Elements of group. Now I have told you which are group 1. This is group 1, 2, 3 to 12. This is 13, 14, 15, 16, 17 and 18. Elements of group 1. So I'll write it here. So elements of group 1, 2, 13, 14, 15, 16, 17. They are called normal elements, or they are also called representative elements. The reason is, if you look at the elements of these groups, what I said, group 1, group 2, 13, 14, 15, 16, 17, we use them in most of our compounds. We see most of these elements in the form of compounds. Most commonly used compounds, elements containing compounds, these are. Compounds containing elements, these are. Right? Therefore, they are called normal elements, or they are called representative elements. Yeah. Then, elements from group 3 to 12, they are called transition elements. They are called transition elements. Yes, this will discuss in the second year topic of chemistry. Right now you understand because there is transition between the properties of metals and to non-metals. In the beginning 3, 4, 5 they are heavily strongly metals. As you move from 4, 5, 6, 7, 8, 9, 10, 11, 12, metallic nature decreases, non-metallic nature. So there is transition from metallic nature to non-metallic nature. Therefore they are called transition elements. Elements of group 18, you have so many names for them. They are called noble gases, or they are called inert gases, or you call them zero group elements, or you call them rare gases because they are present in the atmosphere in very trace amounts. So they are called noble gases, inert gases, zero group elements, or rare gases. Helium, neon, argon, krypton, xenon, radon. These are all called noble gases. The elements here which are placed at the bottom of the periodic table, can you see here these two series of 14 elements each, 1 2 3 4 5 6 7 8 9 10 11 12 13 14. Yes, the elements of the two series of elements which are placed at the bottom of the periodic table, these two series of elements are called lanthanoids, 14 elements, and actinoids, 14 elements. 14 elements. Lanthanoids and actinoids. Yes, these lanthanoids, they are present in group 3. Start from group 3. Actinoids also start from group 3, but here they are present in 6th period, and here they are present in 7th period. I'll tell you what. Yes. Now, coming to very typical representation. Group 1 elements, I said group 1, group 2, they are normal. They are called alkali metals. Alkali metals. The reason is the metals of these elements, the metals present in this group, some of them like sodium and potassium, when they combine with oxygen, all of the metals of this group combine with oxygen and form oxides. But typically these two oxides, when they are dissolved in water, they form water, they form basic solution. Basic solution. Therefore, these metal oxides or the metals are called alkalis. And this is most of the cases. Almost all of them, when oxides are dissolved in water, they form alkalis. Yes, these dissolve completely, but all of them form basic solution. Therefore, they are called alkali metals. Group 2 elements, they are called alkaline earth metals. Alkaline earth metals, because the oxides of these elements also, beryllium, magnesium, calcium, strontium, barium, they also, when they are dissolved in water, they also form basic solution, so alkaline. And these metals are found in the earth's crust in more abundance. Therefore, they are called alkaline earth metals. Alkaline earth metals. Coming to group 13, the first element is boron. Therefore, it is called boron family. Yes, they are named as families. Group 14, the first element is carbon, and they are called carbon family. Group 15, first element is nitrogen, so they are called nitrogen family. Yes, or they are also called pnictogens. Pnictogens, gen stands for producing, pnictogen. Pnictogens, because a property of nitrogen. Therefore, it is called pnictogens. Group 16, they are called oxygen family, or they are very commonly called chalcogens. Gens means producing, chalco stands for ore. So ore producing. If you see, most of the ores of the metals, they are present in the form of oxides, or they are present in the form of sulfides or selenoids. All these elements belong to group 16. For example, hematite ore of iron, Fe2O3, magnetite, Fe3O4, then sulfide, FeS, cinnabar, HgS, mercuric sulfide. All these, they are capable, they are ore forming, therefore they are called chalcogens. Group 17 elements, they are called halogens. Rather than calling a fluorine family, they are called halogens. Why halogens? Because halogens means producing or forming. Halo means sea salts. If you see most of them, chlorides, yes, fluorides, iodides, most of them are produced from the sea salts. Therefore, they are sea salt formings elements. Therefore, they are called halogens. And you know group 18 elements are called noble gases, or their inert behavior, stable behavior, inert gases, or they were called rare gases because of less abundance in the earth crust. Rare gases, okay. If you say rare metals, they are different again. Or zero group elements, because Mendeleev placed them into a group called zero. You will get to know why zero also. So they are called zero group elements. So these are the names of different groups. And what is the special characteristic of a group? Whatever elements, so groups means what? The vertical 18 vertical columns in the periodic table are called groups. Yes, the very special characteristic of the group is that whatever elements come in a group, since they are having same outermost electronic configuration, they are they exhibit similar chemical properties. They exhibit similar chemical properties. That is the typical nature of the groups, right? So the atomic sizes of the elements in the group increases down the group due to increase in the number of shells. The physical properties of the elements such as melting point, boiling point, density, solubility, etc., they follow a systematic pattern. We'll discuss when we discuss about the trends in the periodic table. The elements in each group have generally similar chemical properties. Similar chemical properties. Now, what are periods? Can you see here the horizontal rows? These horizontal rows. Yeah? The horizontal rows in the periodic table. This horizontal row. This horizontal row. So how many are there? 1, 2, 3, then 4, then 5, 6, 7. Yeah, you cannot say 8, 9. Okay, you cannot say 8, 9 because these two, yes, these two, can you see here? 58, it is here only. 57 to 72, there is a gap. 58 to 71 are present here only. So only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 elements plus these 14 elements becomes 32 elements. So this in this horizontal row there are 32 elements. In this horizontal row also there are 32 elements. So how many? 1, 2, 1, 2, 3, 4, 5, 6, 7. So these 7 horizontal rows, 7 horizontal rows are called what? They are called periods. They are called periods. So modern periodic table has 7 horizontal rows which are called periods, and they are numbered with our Arabic numerals 1, 2, 3, 4, 5, 6, 7. Now see here, which is the first element in every period? Okay, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. And which is the last element? The noble gases. Therefore, I can say about the periods. Now we are going to talk about the periods. So I can say that there are 7 periods. 6, 7. So first period has hydrogen, and here helium is there. The period starts with alkali metals, lithium, sodium, potassium, rubidium, cesium, francium, right? And ends with what? It ends with the noble gases. It ends with the noble gases: helium, neon, argon, krypton, xenon, radon. and Og. Yes, so every period starts with alkali metal and ends with noble gas. Please do remember it. Every period starts with alkali metals and ends with noble gas. The first period, yes, the first period has got two elements. Yes or no? One, two. The first period has got two elements and it is the shortest period. It is the shortest period. The second element, lithium with atomic number 3, neon with atomic number 10, has got how many elements? Has got 8 elements. Even if you see sodium 11, argon 18 also has 8 elements. So the second period with starting with lithium and ending with neon, and the third period starting with sodium and ending with argon has got 8 elements each, and therefore these two are called as short periods. They are called as short periods. If you look at the fourth period, starting with atomic number 19, that is potassium, ending with krypton atomic number 36, and the fifth period, starting with atomic number 37, ending with atomic number 54, has got 18 elements each. Has got 18 elements each. And these two periods, fourth and fifth periods, are called long periods. Long periods. Sixth period, starting with cesium atomic number 55, ending with radon atomic number 86, and the last one starting with atomic number 87, ending with atomic number 118. They have 32 elements each. Yes, actually this was called the longest period, and this was incomplete. Very recently this element is being discovered, therefore we used to call it as incomplete, but that also now comes under longest period. It also comes under longest period. Yes, so in all the elements present in a period, the electrons are filled in the same valence shell. The elements which are present in a period, the electrons are filled in the same valence shell. As the number of electrons in the valence shell change, the chemical properties also change. So if the electrons present in the number of electrons present in valence shell, if it changes, then electronic configuration changes. Electronic configuration of what? Of valence shell changes. Therefore, the chemical properties of the elements also change. Is that clear? So this is about the periods of present in the modern periodic table. Yes, horizontal rows. 7 horizontal rows in the modern periodic table are known as periods. In all the elements present in the periods, the electrons are filled in the same valence shell. The atomic sizes generally decrease from left to right. We'll see it. Okay. Apart from these groups and periods, the elements are being divided into blocks. They are being divided into blocks. How many blocks? Yes, apart from periods and groups, the elements is being divided into blocks. Now, on what basis these blocks are made and how many blocks? There are 4 blocks. Now, the question is on what basis the blocks are made. I will take a simple example. Lithium and magnesium. Atomic number of lithium is 3, magnesium is 12. Here I will take scandium, atomic number 21, or I will take zinc, atomic number 30. Then here I will take boron, 5 atomic number. Boron, atomic number 5, or you take fluorine, atomic number 9. Okay. So when you see these elements, examples I have taken, atomic number is 3, 1s2, 2s1. Magnesium 1s2, 2s2, 2p6, 3s2. Correct? Scandium 1s2, 2s2, 2p6, 10 electrons, 3s2, 3p6, 18, 4s2, 3d1, 21. Correct? Zinc similarly 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Right? Boron 1s2, 2s2, 2p1. Understanding? Fluorine 1s2, 2s2, 2p5. See, 5 plus 2 is 7, 7 plus 2 is 9. So when you observe these elements, why I have written the configurations is that if you observe lithium, the last electron is entering into s orbital. Even in magnesium, the last electron is entering into s orbital. In case of boron, the last electron is entering into p orbital. Fluorine, it is also entering into p orbital. Scandium, the last electron is entering into d orbital. Here also in zinc, the last electron is entering into d orbital. If you take after lanthanum 57, 58 atomic number, cerium or something, the last electron will enter into f orbital. Actinoids, thorium, if you take 90 atomic number, the last electron will enter into f orbital. So depending upon the last electron, which is called as differentiating electron. What do you mean by differentiating? It means last electron. The differentiating electron is entering into which orbital? It is entering into which orbital? The elements are grouped into blocks. If the differentiating electron is entering into s orbital, then that element belongs to s block. If the differentiating electron is entering into p orbital, then that element belongs to p block. If the differentiating electron is entering into d orbital, then that electron belongs to d block. And if the differentiating electron is entering into f orbital, then that element belongs to f block. So based on this, we have 4 blocks in our periodic table. We have 4 blocks in our periodic table. Yes, I'll show it here only. Can you see? This block of periodic table is called S block, denoted by small letter. Okay. This block, when you see all the elements here, the differentiating electron will enter into p orbital, except helium. There it enters into s orbital, but there is similarities in all these elements, so it is placed there. If you see in all these elements, the differentiating electron will enter into d orbital, and in these cases, the differentiating electron will enter into f orbital. Therefore, this is called S block, this is called P block, this is called D block, and this is called F block. Yes, now the question arises, why there are only 2 groups for F block, S block? Why there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 groups? Yes, so S block is having how many groups? S block is having 2 groups. P block is having how many groups? 1, 2, 3, 4, 5, 6, 6 groups. D block is having how many? It is having 10 groups. And F block, counted. How many elements? 14. 14 groups are there. Can you just recall where this number is being used? As I said, S block, how many groups are allotted? 2 groups are allotted. P block, how many groups are allotted? 6 groups are allotted. D block, how many groups are allotted? 10 groups are allotted. And F block, there are 14 groups allotted. Yes or no? Why? Can you recall what these numbers are? Yes. S subshell can have maximum of how many electrons? It can have maximum of 4 into L plus 2 electrons. So 4 into L is equal to 0 plus 2. So 4 zeros are 0. And so S block. So S subshell can have maximum of 2 electrons. Therefore, S block is having 2 groups. S block is given with 2 groups. P subshell can have maximum of how many electrons? 4 into 1 plus 2 plus 2. 4 ones are 4 plus 2 is 6 electrons. Therefore, P block is given with 6 groups. D subshell can have maximum of how many electrons? 4 into 2 plus 2. 4 2 is 8, 8 plus 2 is 10. Therefore, D block, so if D subshell can have 10 electrons, therefore D block has got 10 groups. F subshell, 4 into 3 plus 2. 4 is a 12, 12 plus 2 is 14. 14 electrons maximum, therefore 14 groups are allotted for D block in the modern periodic table. See the beauty of this table. So only first S block has got 2 groups. P block has got these 6 groups. D block, these. And F block, it is here. So I can say, so S block, I will take it here. Understanding, clear with this concept. So S block, how do we explain S block elements? Yes, so let us have a view here first. S block. The general electronic configuration of S block is NS1 to 2. What does that mean? See, S block elements, example again, lithium, atomic number 3, and another element from different second group, that is, this is from group 1, this is from group 2, 12. So 1s2, 2s2, sorry, 2s1. Magnesium, 1s2, 2s2, 2p6, 3s1. What does this 2, 3 represent? It represents principal quantum number n. How many electrons? For first group, for group 1, it is s only. How many electrons here? 1. And for magnesium, how many electrons? 2. So, S block elements, they are general outermost electronic configuration is NS1 to 2. And if they ask you general electronic configuration, inside is what? Noble gas configuration, and outermost is, it might be NS1 or it might be NS2. If it is NS1, it is alkali metals. And if it is NS2, it is alkaline earth metals. Alkaline earth metals. Yes. So groups for S block, groups 1 and 2 belong to S block. So 1 and 2 belong to S block. Correct? Okay. So general configuration is NS1, NS2. Characteristics. All the elements are soft metals. They have low melting and boiling points. They are highly reactive. Most of them impart colors to the flame. They generally form ionic compounds and they are good conductors of heat and electricity. Yes. P block. Okay, P block elements. So how do we explain P block elements? Let us consider example. So P block comes from group 13 to group 18. All these elements are called P block. So let us take one example. Boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon 10. We need to understand this. Boron 1s2, 2s2, 2p1. Carbon 1s2, 2s2, 2p2. Nitrogen 1s2, 2s2, 2p3. Oxygen 1s2, 2s2, 2p4. Fluorine 1s2, 2s2, 2p5. Neon 1s2, 2s2, 2p6. Okay, look at this. This is the general, this is the inner core configuration, which will be of noble gas. So I can write noble gas configuration. This is the outermost shell. Please do remember. So outermost shell is having 2s and 2p. Yes. 2 stands for what? If it is boron, it is 2. Below boron, which element comes? Aluminium. If you take aluminium, it will be 3. That's it. 2 is what? Noble gas. This is principal quantum number. There is S, and S is always having 2 electrons. Here, 2 electrons, 2 electrons, 2, 2, 2 remains fixed. Then this is also 2. That means it is also N. This is which orbital? It is P. And here, in case of boron, this is group 13. This is group 14, group 15, group 16, group 17, group 18. So from group 13, it is 1. then it is 2, 3, 4, 5, and then 6. So NP varies from 1 to 6. So if you want to write general configuration for group 13, it is what? It is only NP1. For group 14, noble gas configuration inside NS2, NP2. Group 15, noble gas configuration inside NS2, NP3. Group 17, noble gas configuration NS2, NP4. Group 17, noble gas configuration NS2, NP5. Group 18, noble gas configuration NS2, NP6. So can I say in general electronic configuration of p block elements, p block elements will be what? Noble gas configuration, NS2 is fixed, NP, if it is for group 13 1, group 14 2, group 15 6, 3, group 16 4, group 17 5, group 18 6. So it varies from 1 to 6 electrons. Or if they ask you only outermost electronic configuration, then it is NS2 NP1 to 6. So this is the outermost electronic configuration of all the elements of P block. Characteristics. The compounds of these elements are mostly covalent in nature. They show variable oxidation states. Variable oxidation states. If you take S block elements, the elements of group 1, they can only lose one electron, and their oxidation state will be +1, because when they lose one electron, they gain +1 charge. Group 2 elements, all the elements of group 1 will have +1 charge only. If you see group 2 elements, all the elements of group 2 can lose 2 electrons. So their charge will be always +2, all the elements. Here say lithium, sodium, potassium, rubidium, cesium, francium, all will have +1. Group 2, beryllium, magnesium, calcium, strontium, barium, all will have +2 charge. But this is not the similar case in case of P block. If you take elements of group 13, boron, boron, below boron is aluminium, below aluminium is gallium, indium. In the beginning, all of them show +3. But when you move down, it will show +1. So there is difference in the oxidation state. Therefore, we say they show variable oxidation state. In moving from left to right in a period, the non-metallic character of the elements increases. That is, when you move from boron to carbon to nitrogen to oxygen to fluorine, non-metallic character is more. This is slightly metallic in nature. As you move from carbon to nitrogen, nitrogen to oxygen, oxygen to fluorine, this becomes strongly non-metal. Okay. The reactivity of elements in a group gradually decreases downwards. Aluminium, gallium, indium, thallium, the reactivity decreases. At the end of each period is a noble gas with a closed valence shell NS2 NP6 configuration. So at last we have noble gases with NS2 NP6. Entire shells are filled with these configurations. Metallic character increases as we go down the group. D block elements. General configuration of D block elements. Okay, so D block. Which groups come? Group 3 to group 12 are all D block. Let me take example of scandium 21, and last I will take zinc with 30. In between, exceptional behavior chromium Cr 24 and copper 29. Only these are the exceptions, but these are all common. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Copper 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d4, 5. Sorry, chromium. Copper 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. And last zinc 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Correct? So when you write, see, this becomes the inner configuration, inner core configuration, correct? So inner core configuration is written as noble gas configuration. See, either you can write 3D first, 4s later, or you can write noble gas configuration 4s plus first and then 3D. Okay, doesn't make a difference. So let me say I've written it like this. 4s, S is having how many electrons? Scandium, titanium, vanadium, if you see, all have 2 electrons. But chromium is having 1 electron. Similarly, manganese, iron, nickel, cobalt, if you see, all have 2 electrons, 4s. But copper has 1. So can I say 4s varies with 1 to 2 electrons? And 3D, it varies from 1 to 10 electrons. Yes or no? So this how to write. I can write in general. This is for only first period. If my next elements are also belonging to D block, so I can write noble gas core, which is N here, the last number. 4 is N, so I'll write NS, varies from 1 to 2. D is having, is it 4 again? Here it is 4, here it is 3. 3 means what? N minus 1. N minus 1 D 1 to 10. So this is the general configuration. Or I can write noble gas core N minus 1 D 1 to 10 and NS 1 to 2. So general electronic configuration of D block elements. So here N minus 1 D 1 to 10 NS, it should be not 0 to 2. In some cases of D blocks, it is 0. So it is being given 0 to 2. Not in the cases which I took the examples. Yes, because you know here, right? Okay. So when I say D block, I'm not speaking only about these above elements. All these elements come under D block. So in some of the cases, S is 0 also. Therefore, it is N minus 1D 1 to 10, NS 0 to 2. The characteristics of D block elements. They are all metals with high melting and boiling points. The compounds of the elements are generally paramagnetic in nature. They are mostly form colored ions, exhibit variable valency, oxidation states, and they are oftenly used as catalysts. Very, very, very commonly used as catalysts. So this is about the characteristics of D block elements. Looking at F block elements, which are F block elements which are placed at the bottom. Yes, the electronic configuration is here NS2. So it might be, if it is 5s, this will be N minus 1. So if it is 7s, let us take, this will be N minus 1, 6. This will be N minus 2, 5. Understanding? So N minus 2 F 1 to 14, electrons vary from 1 to 14. N minus 1 D 0 to 1 and NS is always 2. So if you observe, I can say that here with the electronic configurations, general electronic configurations of S block, P block, D block and F block. So configuration here is NS1 to 2, NS2 NP 1 to 6. Here it is NS2 N minus 1 D, sorry, NS1 to 2 or 0 to 2, 1 to 10. And here it is NS2 N minus 1 D 1 to 1 to how much it is? 1 to 0 to 1, and for F it is 1 to 14. So here it is 0 to 1 and N minus 2 F 1 to 14. So here electron is entering into S orbital, so S block, P orbital, so P block, D orbital, so D block, F orbital, so F block. In case of S and P, you can see the electron is entering into the last shell, or I can say ultimate shell, because it is nth shell. Yes or no? Nth shell. In case of D block, if you see, the electron is not entering into last shell. First, this last shell gets filled. Electron is entering into N minus 1th shell. And this N minus 1th shell is called penultimate shell. The electron enters into penultimate shell. Okay. In case of F, you see, it is N minus 1, then N minus 1, and it is entering into N minus 2th shell, the last electron. And that is called anti-penultimate shell. So remember, in case of S and P block elements, the electron is entering into the ultimate shell. In case of D block, it is entering into penultimate shell, that is n minus 1th shell. In case of F block, the electron is entering into n minus 2th shell, that is anti-penultimate shell. Please do remember this point also. Anti-penultimate shell. So what are the characteristics? These are known as inner transition elements because in the transition elements of D block, the electrons are filled in n minus 1 shell, whereas in inner transition elements of F block, the filling of the electrons takes place in 1 minus n minus 2 F shell, subshell. Therefore, they are called inner transition elements. They are present within the transition elements, which happens to be one inner subshell. Characteristics of F block elements. The two rows of the elements at the bottom of the periodic table called lanthanoids starting from cerium atomic number 58 to lutetium atomic number 71, 14 elements, and actinoids starting from thorium atomic number 90 to lawrencium atomic number 103 belong to F block. These two series of elements are called inner transition elements or they are called F block elements. They are all metals. Within each series, the properties of the elements are quite similar. So, till now we have seen in the vertical columns there is similarity, but in case of F block, there is horizontal similarity. There is horizontal similarity. So that was the reason why these two were placed separately. Till now we have seen all these elements show similar properties. All these elements show similar properties. So in the periodic table, there is vertical similarity. Yes. But in case of F block, there is horizontal similarities. They show similar properties. So that was one reason why they were placed separately. Now you may say, you could have placed them in this 6th and 7th period only and you could have explained horizontal similarity. Of course, we could have explained, but unnecessarily, only the 6th and 7th period would have become longer. It would have got expanded. So to avoid unnecessary expansion, they were placed separately. So these were the two reasons why F block elements were placed separately. Why these F block elements were placed separately. Yeah. So most of the elements of actinoid series are radioactive in nature. That is, they emit radiations on their own. They emit the radiations on their own. So till now we have discussed that the periodic table is being given based on atomic number as a fundamental property. It is being classified as the periods and groups. There are 18 vertical columns called groups, and the special characteristic of a group is that all the elements which come in this group have similar properties. Periods, the 7 horizontal rows are called periods. The special characteristic is that each period starts with a alkali metal and ends with a noble gas. And then even we have seen it is being divided into blocks depending upon the differentiating electron is entering into which of the orbitals, say S block, P block, D block and F block. In case of S and P block, the electron is entering into nth shell, that is the ultimate shell. In case of D block, the electron is entering into n minus 1th shell. So we call it as penultimate shell. And in case of F block, the electrons is entering into n minus 2th shell, which is called anti-penultimate shell. So the next part of this chapter we'll take up in the next video. Hope you have understood. You have got with all the concepts. Please practice them. Thank you.